in my PowerPoint notes, I give you 4 examples, but I only did 3 of them. The 4th one, I plan to skip it because it's a special case of one of the examples today. Today we have a more general case. So let's just do that general case. It includes that special case. So we can save some time. Yeah. All right, so let's start the first question. Yeah. 2.5. Yeah. Show that n to the dth power function here, okay, belongs to little o. I hope you still remember this little o notation. Little of exponential function a to the nth power. Yeah. Here the condition, d greater or equal to 1, non-necessary integer. No, here we only need d greater or equal to 1, non-necessary integer, and a strictly greater than 1. Yeah. This result also quite basic, yeah, and pretty important. Yeah. Here you can see this little notation tells us this fact: the exponential function a to the nth power of m with n greater than 1 dominates any power function, n to the d power function. Okay, yeah, all right. So here, in order to make our proof easier, in my proof, I assume d an integer greater or equal to 1. That would make the proof easier. But this result is also true for non-integer. For non-integer, we just need one more step on integer. Yeah, so I will show you after we finish this integer version, then we just add one more step, we can get a non-integer version. Yeah, so don't worry. Yeah, so let's do the integer version first. All right, how to do it? Little o, we need to take the limit. When you see little o, the only way we can use little limit method, yeah, for this little o. Yeah. But we need to use the continuous variable. Here you can see I switch to continuous variable immediately. Okay? Yeah. So we know the reason, because we want to take the derivatives based on the L'Hopital's rule. All right? So limit x approaches infinity, x to the dth over a to the x. Then, can I check a little bit here why we can take L'Hopital's rule here? Can you tell me what's the reason this is the appropriate situation that we can take L'Hopital's rule?
It's infinity over infinity.
Great, infinity over infinity. We call it indeterminate form. Infinity over infinity. Yeah, let me write here. Check that first. Because if you forget to check, sometimes you can get a wrong answer. Yeah, later I will show you. Sometimes we may get a wrong answer if you forget to check. Yeah, you will see at the end, you will see. Yeah. All right, so let's start. Let's take the L'Hopital's rule the first time, because for this question, we need to take it multiple times, not just once, multiple times. The first time, do you remember For the power function, the derivative, there is a power rule. Yeah. I wrote on notes before, and here we need to apply that power rule again. Yeah. Power rule. Remind you for the derivative. Yeah. X to the rth power. Yeah. We want to take a derivative of this one. R here we treat as real number. All right? Real number. Could be negative, not necessarily positive, right? Could be negative. Yeah. Could be, you know, irrational number. Yeah. It doesn't matter. Yeah. Its derivative equals R times X to the R minus 1. So this is the power rule. All right. Here, let's apply the power rule on X to the dth power derivative. That is d times X to the d minus 1. Numerator, denominator, the formula, constant part, natural log of A. It's positive because A greater than 1. So natural log of A is positive. Then multiply the original exponential function, A to the X. All right. After this step, you can see still it's not easy to see what is the limit, right? It's still hard to see what is the limit, okay? Because if you check, it is still infinity over infinity. So it's another time we need to apply L'Hopital's rule. So the second round derivative, another round. Second round, power rule again, this time d times d minus 1 times x to the d minus 2 power. All right? Denominator, we just multiply another natural log of A. The second round. So if, you can see, so if the power function x to the d minus 2, if it's positive, the exponent is positive, it's another infinity over infinity indeterminate form. So we should keep applying L'Hopital's rule again and again until at some point we stop. Otherwise, we keep applying L'Hopital's rule. To some point, that is not indeterminate form. The place that we need to stop when it is not an indeterminate form anymore. Yeah. Let's look at this step. After we apply d times d integer, so here we need integer. Otherwise, if d is not integer, we cannot stop, right? Think about that. If d is not an integer, then we have to keep going forever. You know, we get trouble, okay? So for this reason, we assume integer value for d first. It's a big step. But the second step, smaller step, we complete the second part, small step. Yeah. All right. Here, now, when you look at this current fraction form, limit. Now, can you say it again? It is still an indeterminate form? Constant. The numerator is constant. Now you should be careful. Don't apply L'Hopital's rule again. If you apply it, yeah, because some of you may forget that condition check, right? Indeterminate. You apply derivative on the numerator, you get 0, right? You get 0. No, that is wrong. Okay, yeah, here. But here the answer, the numerator is not 0, it's constant d factorial. d factorial numerator. But denominator goes to infinity, right? Denominator goes to infinity. So constant over infinity, the answer is still infinity. After the simplification, answer still 0. The limit is 0. Yeah. But we need to make sure every step our logical reasoning must be correct. Okay? Yeah. I don't want to see some of the steps you make wrong logical reasoning, but your answer is correct. We're not satisfied with that. Okay? Every step you have to make correct logical reasoning. Yeah. Okay? Yeah. All right. So then we get a conclusion, little o. N to the d belongs to little o of a to the n. Yeah. That's the big step we make. Then there is the remaining part, just a little more work. Yeah. Remaining part, yeah, let me say in this way. Yeah. Because this time we need to assume not integer, right? D not integer. Sorry. If D not integer, we know, yeah, let me write. If D is not an integer, then can we round it up to an integer? Round it up to an integer. How about that? Round it up, not round it down. Yeah, although we can round it down, but we would rather round it up. Okay? Round it up, let's use the seeding function. Seeding function. That means d is less than seeding function of d, right? But d, the seeding function of d is an integer, right? The seeding function of d is an integer. Now let me write the new limit. You can see the new limit. Limit n goes to infinity, n to the d over a to the nth equals I split, all right, yeah. The first limit, n to the d over n to the ceiling function of d. How about that? Okay, n to the d over n to the d ceiling function. All right, second limit, numerator n to the ceiling function of d over a to the n. How about that? Product of these two limits. Now you tell me, what is the limit of each limit there in the product? What is the limit of the first limit in the product? The exponent of the denominator is greater than exponent of the numerator, right? Yeah, that means it's 0. And the limit of the second one we just proved. Seeding function of d, it's an integer. We proved the integer version, right? Yeah. So the second one also 0. 0 times 0, it's 0. Yeah. So we make it. Yeah. From this example, you can see. Yeah. Many times we need to do a simpler version. D, original D is not an integer, but when we start, we want to work on a simpler version. So we assume D is an integer. But after that, that's not our destination, right? That's not our destination. If you compare with our destination. This is intermediate result. If you compare it with our destination, there is a small gap. So our second step, we need to bridge that small gap. Yeah, so here we need to use this limit property. Yeah, this limit property. Yeah, so we bridge that gap. Yeah, so we complete the whole proof. How about that? Yeah. The conclusion is important. Conclusion. Yeah. Conclusion. Yeah. Let me make the conclusion after I finish these examples. Yeah. Conclusion important when you work on some of our homework questions. When you work on some of our homework questions. Yeah. Yeah. Remember this result here. Okay. Yeah. All right. Next. 2.6. Yeah. All right. Yeah. So this time. Yeah. Sorry. Still, yeah, space not enough here. All right. Show that log base 2 of n belongs to little of root n. Root n. Yeah. Same method. Yeah. So then let me just apply it. L'Hopital's rule, but on a continuous variable functions. Okay. Yeah. Infinity over infinity, no problem. Right? Yeah. So we check infinity over infinity. So we can apply the L'Hopital's rule. Before we apply it, let's write root of x as a power function. X to the 1/2 power of 1/2. Power 1/2. Okay? Yeah. All right. Then numerator derivative formula 1 over bracket natural log of 2 times x. The formula. Yeah. So if you cannot remember, just search somewhere. Okay? Search web or calculus book. Okay? All right. Denominator power rule. This time you can see it. Yeah. We just use the power rule. Okay? Yeah. After simplification, now you can see it's not indeterminate form. Numerator is constant. Denominator goes to infinity. So the answer is 0. Then we go back to the discrete variable version, our conclusion little o. Okay? Yeah. Yeah. All right. Then the last example of this part, 2.7, this time natural log belongs to little of n to the d power function, n to the d. And here, what's the condition for this d? Exponent number. We only need a d positive. That's all we need, greater than 0. Non-necessary integer, and yeah. That's the general case. Okay, so this is the general case. Let's apply L'Hopital's rule. Infinity over infinity, no problem, right? Yeah, so that's easy. Yeah. Then derivative, numerator, the derivative of natural log reciprocal of x, 1 over x. Denominator power rule, d times x to the d minus 1 power. Yeah. After simplification, we get this. It's not indeterminate form. Constant 1 over d times x to the d power. All right. When x goes to infinity, because d is a positive number, x to the d also goes to infinity. The denominator goes to infinity. The whole fraction goes to 0. So our conclusion, natural log of n belongs to little of n to the d. Yes. So these 3 examples. Yeah. First, we review that L'Hopital's rule. But in my assignments, I will not give you a L'Hopital's rule directly. Okay, yeah. Here we mainly use L'Hopital's rule to help us get these results. Yeah. We have rigorous proofs. Yeah. Then you can apply the results with a lot of confidence. Okay, yeah, all right. Then my comments. Yeah. Comments related to homework assignment. Yeah. This part. Yeah. Because the reason it could be important, because if you do not understand these comments, you may get a delusion, not intuitive. Yeah, I will show you, not intuitive. You will get some delusion. Okay, yeah, all right. So here, let me give you some comments. First, regarding the question, example 2.5. Yeah, all right. Here, that d, the exponent number d, could be very large, right? No, because we only need positive. Greater or equal to 1, that's not important. Any positive d, we can put there. Okay, yeah. So think about, we make that d equals 1 million. How about that? Oh, I noticed some lagging problem. Yeah, even this panopto, I noticed some lagging problem. Yeah, all right. Look at that. N to the 1/millionth power. All right, yeah. Then a, how about a, we only need greater than 1, strictly greater than 1. How about 1.000 many 0, 1? How about that? Very close to 1, right? With so many zeros after the decimal point. So small. All right. But based on our result, if you think our result is correct, yes, it is correct. Okay. So this function belongs to little of 1.0000001 to the nth power. Can you see it? Can you see it? Right? Not quite intuitive, right? Not quite intuitive. Yeah. Think about that. Because you may feel this function close to 1. You may feel, how can this function value very large, even greater than n to the 1/millionth power? Is that possible? Yeah. But mathematically, when n is sufficiently large, it's correct. When n is sufficiently large. Yeah. Some students, they use very powerful computation software. Okay, for example, Wolfram Alpha. Some of you may have heard of that, right? Wolfram Alpha. You go to the website, so you can use the Wolfram Alpha to do some sophisticated computation. Yeah. Some students use the Wolfram Alpha to compare these two functions. Yeah. Because it's very hard to make n very large. So what they see, the first function much higher than the second one, but for us, we cannot go very far, right? How far you can go, think about. You cannot go very far. Yeah. So you cannot see the place that second function dominates the first one. Yeah. Because our vision is too limited. Okay? Yeah. Our vision is too limited. But here the number for n unlimited. Yeah. Yeah. There is some point. The second function dominates the first function will be correct. Yeah. But it's hard for you to imagine. So for that reason, if you do not understand this part well, you may get a wrong answer. Yeah. Our homework, we will have this kind of questions. You may get a wrong answer. So be careful here. So that's the first example. Second one, look at the example 2.7. This time, natural log of n belongs to little of n to the d. That d we only need positive, right? If it's positive, yeah. So for the second one, okay, yeah. So this case, can we make that d equals 0.000001? Can we make that? We can, right? Yeah. Even if we make d this small, we know it's positive, greater than 0. But we still, based on the result of this example, we have natural log of n belongs to little of n to the 0.000001. How about that? How about that? Okay, the power function exponent is extremely small, but still, sooner or later, it will dominate. It will dominate log function. Yeah. Hard to imagine, but it's correct. Hard to imagine. The reason is our imagination is very limited, right? Yeah. Our imagination could be very limited comparing to the universe, right? Yeah. Because here you may go very far in the universe. So that's the reason. Hard to see. A lot of things hard to see. Okay? Yeah. So give you these two examples. Yeah. Not quite intuitive. Yeah. But if the proof is correct, then the result must be correct. Okay? Yeah. All right. Any question? Yeah. So we finish. This is module 2, so we'll finish module 2. So then we start our new module, module 3. Yeah. 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 So we need to all right, yeah. Recursive algorithms, the whole module. Yeah. It's very important, very fundamental. Yeah. So we need to really understand this type of important algorithms. Part A, Introduction to Recursive Algorithm. 8.1, First View of Recursive Algorithms. Yeah. Recursive thinking. Let us try to make our thinking adapt to recursive thinking. Yeah. We need to get used to this kind of thinking. Yeah. All right. Question: why recursive thinking is important in problem solving? Yeah. All right. We are used to straightforward, non-recursive thinking, yeah, in problem solving. So if you do not get a training in this way, yeah, very likely you do not do recursive thinking, okay? Because you like to do straightforward thinking, not recursive, okay? Yeah. So in this module, we will get a training in this recursive thinking. Yeah. Some problems can be solved in both ways. First, non-recursive way, second, recursive way. These two ways. And here I like to compare a little bit. Yeah. Each one has its advantages and disadvantages. Yeah. All right. But the most important reason we want to use the recursive algorithm because of this one. Power of recursion. Power of recursion. It is very powerful. This method is very powerful. So we want to use its power. Power in problem solving. Yeah, you will see it. We have many examples. You will see the power. Okay? Yeah. Some relatively hard problems can only be solved by recursion. Can only, here I put a parenthesis around only, yeah, yeah, because it's slightly different from our textbook. Our textbook says all computing problems can be solved by non-recursive way. Theoretically, yeah. But you will see many problems. It's hard to imagine non-recursive way to solve. Yeah. Later we will see such problem. Yeah. So that's why I put it in the pair of parentheses. Yeah. Extremely hard. So we don't even try it. Non-recursive way for those hard questions. All right. Here, let's do comparisons a little bit. Iterative, non-recursive, usually we do iterative way. Yeah, for loop, iterative way. Yeah. Then recursive. These two basic methods. Let's do comparison a little bit. Yeah. Iterative way, usually it uses less resource, less computing resource. This is its other advantage. Less resource. Yeah. Yeah. Save computing resource. Yeah. I will explain this part a little more. Yeah. But harder implementation for hard questions, not for easy questions. Harder implementation for hard problems. Still, the lagging problem, yeah, probably a little better than Zoom, yeah. Still, recursive, it uses more resource. Yeah. That's a disadvantage, but easier implementation. For a lot of harder problems, implementation easier. Okay, yeah. So you can see, yeah, advantage, disadvantage, yeah. So here, I like to explain why more resource. Yeah. To understand this part, you need to understand internal implementation of recursive algorithm. Internal, inside computer. Yeah. When we use the modern high-level programming languages, Java, C++, Python, and many other modern programming languages, they all support recursion. They all support recursion. But if you know the history of programming languages a little bit, early programming languages, most of them, they did not support recursion. Early programming languages. Okay? Yeah. Yeah. So that means in order to support recursions in the programming languages, you need to do some special resource arrangement in main memory to support recursions. Yeah. So here, let me give you that part information. Yeah. So here, let me explain the more resource. Okay. So in computer main memory, yeah, in memory. So we know. So yeah, that's the working environment, right? In order to execute your programs. We need a special data structure to support the recursion. That data, you have learned the stack data structure. Stack data structure, you know it, right? First in, last out, right? First in, last out. Last in, first out, right? So it's main property. First in, yeah. Fi, first in, last out. Yeah. Because you push item into the stack. Okay? Yeah. Into the stack. First in at the bottom. Okay? 1, 2, 3, 4, 5. Last in at top. So, but when you retrieve the values, you do it from top. Okay? From top. So the first in, last out. Last in, first out. So that's its main property, the stack. Okay? All right. Now, when you do recursion, now think about it. You need to do recursion. Now here, let me draw the diagram how to do the recursion using the stack data structure. All right. Suppose we use this stack to do data structure, to do recursion. Yeah. For recursion, we want to evaluate function f of n. But we couldn't find its value. We need to do recursion. It relies on its previous value, f of n minus 1. Yeah. So f of n is not available. So the implementation mechanism push it into the stack. Yeah. Put a hold a little bit. Okay. So push it into the stack at the bottom. Okay. F of n at the bottom. Yeah. So, and f of n minus 1 should be evaluated earlier before f of n. But f of n minus 1 still not available. Push into f of n minus 1 into the stack another time. And so on. Right? Yeah. So you push in dot dot dot. Okay? Yeah. Then the last one, you need the value f of 1. It is available. Yeah. Because the initial value is given. Yeah. F of 1 available. So you use its value. After you get f1 value, then you need to retrieve f2 value and do operation. Then you retrieve f3 from the stack, do operation, and so on, until you process the whole stack. In order to get a bottom value, you need to do the computation from top to bottom, the whole stack. You use a lot of resource, right? Yeah, because the stack in the main memory could be very deep. Yeah. The stack could be very deep. the deeper the stack, the more resource to be used. Yeah, deep. Yeah, very deep. It consumes a lot of your memory resource. The more memory resource is used, the slower your algorithm. Yeah, too much resource used, the slower. Here, so you can think about here why my handwriting is so slow. Because the software does not manage the memory resource efficiently. Okay, it managed, in some bad way. Then it consumes a lot of resource. Then when I do handwriting, it becomes very slow, slower and slower. That's the reason. If it manages memory efficiently, then I can write very smoothly. Okay? Yeah, that logic. Yeah. So here you can see this drawback actually pretty big, right? Yeah, pretty big. Yeah. Have you heard of stack overflow? Yeah, you heard of stack overflow, this term. So if you consume too much, if your stack is too deep, you could get overflow on your stack, right? Stack overflow. So the whole computation is dropping. If stack overflow occurs, the whole computation must be dropping. You couldn't complete your computation due to the stack overflow problem. All right? Yeah. Yeah. All right. So, but you may ask this question. Recursion, it could cause this big problem, but why we use it? Answer, we like its power. Sorry, yeah. 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 We like its power here. Yeah. The power is so big. The power is so big. So we would rather accept this kind of drawback. Okay? Yeah. We hope we can control the memory usage in an efficient way. We try our best. But we have to take advantage of its power. Yeah. All right, yeah. So that's the recursive thinking basics. All right. Then let's work on our first recursion problem. The first one is very simple example, but we can learn a lot of basic concepts. Yeah. Calculate the factorial. Yeah. You know how to calculate the factorial. Yeah. Given a non-integer, non-negative integer n, we want to find its factorial, n factorial. All right. You can use a for loop to calculate easily, right? You do not need a recursion. Yeah. But here we want to do a practice, use recursive thinking here. Okay. All right. Yeah. Method one, iterative way. Yeah. So we just apply the definition of n factorial. Yeah. Product of these n consecutive integers. Yeah. Yeah. But here we need to make this assumption. 0 factorial equals 1. 0 factorial. Here, this is our assumption. Zero factorial equals 1 assumption. Can you imagine that? Because we want to understand why 0 factorial is 1. Yeah. Based on our intuition, it looks like 0, right? 0 factorial. Because you do not have a chance to multiply non-zero numbers. How can you get 0 factorial non-zero number? All right, not quite intuitive, yeah. But here, another important thing. So when we make assumption like this, we cannot make a random assumption. We cannot make arbitrary assumption. We have to make assumption that is compatible with this whole definition of n factorial. Compatible with the definition. Otherwise, your assumption is incorrect. Your assumption is incorrect. Yeah. Yeah. So later we will see this assumption is correct. Yeah. And not easy to see. Yeah. But we will see it. Yeah. All right. Yeah. So we delay to the next slide. Yeah. Implementation. Implementation, method one, just the one for loop. Yeah. So you can do it easily. Yeah. Now I like to practice recursive thinking on this simple question. Method number two. Yeah. Recursive way. Yeah. The main idea here, how to do recursion. Yeah. Because the formula is not recursive. So we need to convert this formula to a recursive version first. Then we can define our recursive function. Yeah. All right, so here we take some general problem-solving approach. Recursive thinking, yeah. Here, the place. How we do the recursive thinking here. All right. Divide and conquer approach. Divide and conquer approach. Yeah. A very important method in problem solving. Now, here we see this idea, but our module 4, the whole module is devoted to divide and conquer. Yeah. So we will spend a lot more time in module 4 on this topic, divide and conquer. All right. Yeah. So here we use this fact that we used it before. The problem is easier when the size is smaller. Remember this fact, this is a general principle. So we say in general. Yeah. Still a big lagging problem. Yeah. Anyway, yeah, yeah, not very good. Yeah, yeah, all right, yeah. So when you work on a problem of the current size, assume that the problem of a smaller size has been solved. Yeah. So here we build our solution. Step by step. Yeah. Every time we work on a problem with a certain size, there is a size number. But when we work on the current problem size, we assume there is a smaller problem size version has been solved. And that solution could be used for the current problem size. That idea, recursion idea. Yeah. All right. Yeah. So then, but there is a gap, right? Previous problem size, current problem size, there is a gap. So then we need to fix the gap through a recurrence relation. Yeah. So if you find that recurrence relation, then you're almost there. Because you can write a definition of your recursive function based on this recursive relation immediately. Okay? That step is pretty straightforward. So you can see the most important step is this step. This step is the most important. Derived recurrence relation, the key step. Yeah. All right. Yeah. So let's look at this example. Yeah. How do we apply divide and conquer approach on this formula? Okay. Yeah. Yeah. The idea pretty straightforward. Yeah. Divide. We need to do divide step first. How to do the divide step? Yeah. Let us assume. Let us use the notation f of n represent the original factorial function, f of n. Yeah. All right. Then divide step. Yeah. This vertical line, it's a divide line. So we divide our data in two parts. Okay. After this cut, we split our data. Yeah. These numbers, our data. We split our data into two parts. The first part, n minus 1 numbers. Second part, only one number. Okay. That's the divide way. Yeah. One of the divide ways. Okay. All right. After this divide step, then the first part of the data, the product of all these data, we can use our definition of the factorial. That is f of n minus 1. n minus 1 factorial, the definition. So we use the f function, capital F function, f of n minus 1 to represent the first part operation on the data. Okay, yeah. Then the second part, just the n, yeah. So we get this formula, recurrence relation formula, the key formula here. F of n equals f of n minus 1 times n. Yeah, this formula. Okay, yeah. What's the benefit? Yeah. What's the benefit of this formula? Not much benefit here, not much benefit in computation efficiency. Yeah. But one thing is different. You change the view a little bit, right? Yeah. You change the view a little bit. Although for this simple question, we do not need recursion for this simple question. But for learning, for education, yeah, we like to view it in this recursive way. Learning purpose. Yeah. All right. Yeah, so here n greater than 0. We get this formula. So do you believe this formula is correct? You believe it, right? Yeah. Yeah. Because equivalent from the original formula, right? Equivalent. Equivalent. Okay? Yeah. Yeah, it's correct. It's correct. Okay? Yeah. And implementation is easy. So here I do not need to tell you how to implement this recursion. Yeah. Yeah. So that's not important here. Yeah. All right. But here I like to use this formula to explain this question. How to see 0 factorial equals 1. How to see it? Yeah. Because it's not intuitive. It's not intuitive. Yeah. Not easy to see. Yeah. But with this formula, you can see it easily. With this new recursion formula, you can see the compatibility of this assumption with our original formula. Yeah. Let me show you. From this recursion formula, we can write it as f of n minus 1 equals f of n over n. Okay? Yeah. F of n over n. That's the simple algebra operation. Yeah, no problem. It's correct. We divided by n both sides. n not 0. So we have no problem to do this division, right? Because n not equal to 0. We do not allow n 0, right? So no problem to do this division. All right. Now you plug in n equals 1 into this formula. N equals 1 into the formula. Left-hand side, f of 0. Right-hand side, f of 1 over 1. F of 1 factorial. 1 factorial is 1, no problem, right? 1 over 1 equals 1. But the left-hand side, f of 0, it corresponds to 0 factorial, right? F of 0 corresponds to 0 factorial, based on the definition here, right? Based on the definition here, n factorial corresponds to, 0 factorial. Although, in our original definition of the function, we do not, here. In our original function, we may not have 0 factorial clearly defined, right? Yeah, clearly defined. But here you can see, based on this formula, if we assume 0 factorial as 1, it is compatible with the original formula. The compatibility comes from this recurrence relation, recurrence formula. Compatibility. So it's not wrong. That's the reason our assumption is correct. Okay? If you get a contradiction for your assumption with your original formula, you get a contradiction, then you cannot make that assumption. Okay? Yeah. Here, no contradiction. Yeah. All right. Yeah. So any question? Yeah. Yeah. So in this way, so you can see, yeah. This is the first time we apply this recursive thinking as a practice exercise, because this computation problem is so easy. We don't need a recursion here. Yeah. But before we work on harder questions, so we like to get some warm-up exercise on recursive thinking. Yeah. Our next question will be a very hard one. Definitely today we cannot solve it, but today how about let me give you the question. Next time we do the solution. Yeah. The question, most of you did it before, I believe, when you are small kids. Yeah, you did it. Yeah. So let's look at the question. Yeah. All right. 8.2, I want to show you the power of recursive algorithms. Power. So from this example, you will see if you do not apply recursion, you may not be able to solve it. Most people may not be able to solve it. Yeah. All right, so let's look at the question. Problem 7, Tower of Hanoi problem. So you may have heard of that. Yeah. So, yeah. Actually, in your 2250 class, you learned this example because I took some of the materials from that class. Yeah. When I taught that class, yeah, I taught that before. Yeah. So I took the material from there, but here because we focus on recursion, we want to understand recursion, the power of recursion, so we use this example again. Yeah, it's also in our textbook. Yeah. So that's the reason I use this again. All right. So from this picture, you can see the puzzle. This puzzle. Yeah. Yeah. To play this puzzle, we need to apply 3 rules. So let me describe these 3 rules. Yeah. How to move 3 disks from the first peg to the last peg. You only have 3 pegs. Yeah. So all right. The rule number 1. Only one disk can be moved at a time. Okay, one disk at a time. Okay, yeah. Not a whole stack. Okay, yeah, multiple disks. No. So the first rule, simple rule. All right. Second one, a disk cannot be placed on top of a smaller disk. Yeah. 3 disks with different sizes, biggest, middle ones, the smallest. Yeah, but every time you put one disk on top of another one, you need to make sure the lower disk must be greater than the higher disk. Yeah. Yeah. That order, you need to make sure the order is right for your move, legal move. Okay? All right. Rule number 2. Number 3. Yeah. All disks must be stored on a peg except while being moved. That means you cannot use table, you cannot use other places to temporarily put your disks. Yeah. When you put your disk somewhere, it must be on one of the 3 pegs. Yeah. Otherwise, too easy, right? So you use a lot of space on the table. That's too easy. Yeah. Not challenging. Yeah. So with these 3 rules, then it becomes quite challenging. Yeah. But not too bad. A little challenging, but not too bad. Yeah. And we will get a solution next time. But before you leave, yeah, I just finished the last sentence. This 3-disk version. Here it's the 3-disk version, right? Yeah. But that's not our goal. Our goal, we need to solve N-disk version. That's the final goal. Yeah. Final goal. Okay? Yeah. So solve the N-disk version. Okay? Yeah. But for N-disk version, yeah, so we, in the original stack, we put N disks. Okay? Yeah. In order, that order, but even for N disks, you can only use with 3 pegs. N disks, it does not mean you also increase the number of pegs to N. Otherwise, too easy, right? Yeah. So not N pegs. Still 3 pegs. That will be very challenging. Think about that. Okay? Think about even 10 disks. Extremely challenging. 10 disks. Yeah. But if you want to try, you can try 3 pegs